Okay, so good morning. So we can we're going to start now the second part of the morning session. So our first speaker is Carlos Arguelles from La Plata University and ICRANet. He's going to speak about the dark matter fermions from nonlinear to nonlinear structure formation. So Carlos, please proceed.
Okay. Thank you, Jorge. Thank you. I would like to thank you, the organizers, for this meeting, in particular Sorush, which has been very kind. And yes, today I will speak about dark matter fermions and how, by assuming a spin 1/2 neutron fermion in the early universe at decoupling, we can understand the formation of linear, but also the nonlinear structure formation. So these works I will present here, you can see down in this slide, and has been done in the last years with the collaboration with the ICRANet people, Professor Ruffini, Professor Jorge Rueda, and the postdocs Andreas Krut, and now Edward Becerra, and also my student Rafael Yunis. So let's start. Let's assume, as I said, that after the inflationary epoch, we have a neutral fermion, massive of spin 1/2, which decoupled from primordial plasma, generically speaking, which could be either in a relativistic or non-relativistic manner, and then evolve in the expansion and evolution, and when the universe was cold in lowering down the temperature, and thanks to the primordial density perturbation in cosmological perturbation, the overdensity start to conglomerate in the seeds, what will be the seeds of the cosmic web, which later on in the last age of the part of the universe, the baryonic matter start to fall inside the potential well of this dark matter potential and form the galaxies that we see today. So the challenge will be to understand by theoretical means how this neutral fermion can evolve and form the cosmic web, and then how also can we understand the galaxies that we see today. So let me first start for the success of the lambda cold dark matter paradigm on large scales. This lambda cold dark matter is understood as a cold and collisionless fluid, and the main results can be understood in terms of the astrophysical observations, such as CMB, BAO, Lyman alpha forest, and local distribution and evolution of galaxies, which are ranging from horizon scale of the universe until scales between galaxies, all lead to a universe which is consistent with a scale invariant primordial spectrum, and that is dominated by dark energy 70%, following by 25% of cold dark matter, and only 5% of baryons plus radiation. This is when it's covered the lambda cold dark matter cosmology. And one point I would like to highlight here is that from cosmological perturbation theory within the lambda cold dark matter paradigm, we can constrain very well the amount of dark matter in order to reproduce the CMB, which is the picture you see here on the right, with these very tiny fluctuations in temperature. For 1 in 10,000, you can see in the power spectrum of the temperature variation here in this plot, and you see that, for example, if one will put less amount of dark matter that required, the data you can see here is the Planck fit is in the black dash, but if you will put a less amount, the relation between a second and third peaks of this spectrum of temperature fluctuations changes considerably with respect to what is observed, and not also the heights, but the positions of the peaks, and also you would put more dark matter when needed. This relation shifts as well, and so this result has been is the claim is the result of most compelling evidence of non-baryonic matter in the CMB, and so it opens it goes for the need of dark matter. So, but then we can move to the local universe from redshift around 0.1, as you can see here in this map of the distribution of galaxies in our local universe. where we see that the galaxies are not distributed in a homogeneous way, but forming a cosmic web, where we can recognize filaments, nodes, and voids. And for example, if we point to a node here in the cosmic web, and we see this picture to the top right, we can see a halo, for example, on a scale of hundreds of kiloparsec. This is an example from a simulation. And this halo implies that the so-called rotation curve of this galaxy, the circular velocity of stars in the surroundings, had to move. We can see that they cannot be, this rotation curve cannot be explained only by baryonic matter, because this is the baryonic matter curve is this expected trend in dashed white line, which is a Keplerian trend in the outer parts. But instead, the observations show a nearly flat or sometimes rising part in the rotation curve towards the outer part of the galaxy, which is, therefore, it is also the need for existence of a dark component of matter, which we are here, we'll try to understand in terms of the self-gravitating fermions. So let's go now from a bit of theory. So by assuming this dark matter fluid as a collisionless particle system described by mean field Blasov-Poisson equation, this equation you can see here. This is the equation, probably as you know, that is typically is the first starting point from n-body simulations equation, which is treated there as a fully numerically. Here we will follow an alternative approach in which we will try to start from this equation, but trying to obtain the most likely coarse-grained phase space density of the particles at relaxation. And therefore, in order to do this, we can separate the fine-grained phase space density, this F we can see here, into a coarse-grained part and fluctuation, F tilde, and replacing the Blasov equation. So when this is done, we can obtain a similar equation of the Blasov-Poisson. So the left-hand side is resembles the Blasov equation, but in terms of the coarse-grained phase space density, and we put all the fluctuation average in the right-hand side, leading to this diffusion current. So this is the gradient of the diffusion current with respect to velocities. So this is a very complicated equation to solve because it's a time dependent, but it can be solved by in a clever manner by asking J to fulfill macroscopic constraints such as first and second law thermodynamics at coarse-grained level. So E dot equals 0 and S dot coarse-grained entropy larger equals 0. This is the form of S dot is in terms of form of a Lindenberg entropy. And this was called as a maximum entropy production principle. It was first understood by full mathematical means by Chavani in 1990. And interestingly, during its evolution, the system maximized its rate of entropy creation while satisfying the constraints fulfilled by the dynamics. Therefore, what Chavani showed is that by using this maximum entropy production in this convection diffusion equation with this J, plus the quasi-linear theory developed by Russian scientists some years before, we can go from that convection diffusion equation into a modified Landau equation, which is this one we see here. This resembles somewhat the Fokker-Planck equation, but has a nonlinear term in the coarse-grained phase space density that you see in the third term of the equation of the left. And when the diffusion current is J is constant, meaning it is have to be interpreted as the system evaporate particles in a constant rate, it is possible to obtain an analytic expression for the most likely coarse-grained phase space density stationary, so independent of time, which is of the Fermi-Dirac type. And this generalized the work of Lindenberg, which probably you have heard in the late 60s, where he introduced the physics of ion relaxation, but in a more in a heuristic manner, so without proving how it can arise from a kinetic theory approach, which was down here formalized by Chavani and extended for escape of particle effects, because you can recognize the Fermi-Dirac distribution in the denominator here, but in the numerator we have a a term that for energy is larger than EM, which is can be interpreted as escape energy. So the distribution function is zero, right? It's no particles. Interestingly, this approach was extended for indistinguishable particles because originally Lindenbell was thinking this for as statistics for stars, relaxation, but then it was extended for indistinguishable particles such as neutrinos 2 decades later, and in particular we will use it for fermions, which in this case the maximum accessible value or occupation number, eta 0, is in terms of the HQ, as you see here, and proportional to the particle mass to the fourth. Therefore, once having this most likely phase space density relaxation from this maximization entropy principle, so we can try to build halos at thermodynamic at equilibrium, right? So the first key point to understand is that fermions under self-gravity do admit a perfect fluid approximation. It was demonstrated in this first paper, Ruffini and Bolasola, in the 69 by solving Einstein-Dirac, and therefore it is allow us to solve the equation of a semi-degenerate gas of fermions in hydrostatic equilibrium, and therefore solve the Tolman-Oppenheimer-Wolff equation in spherical symmetry. So you see here, the first equation is the mass equation, the second equation is the Tolman-Oppenheimer-Wolff equation. So these two are Einstein equation in spherical symmetry. Nu is the metric, the temporal metric of the system. And then we have the third and fourth equation are Klein and Tolman equations. So equations of zero and first law of thermodynamics. This you can recognize this in Tolman equation. These all are written dimensionless, and I will show right away the magnitudes associated. And the fifth equation is energy conservation along geodesics. So now we have a coupled system of differential equation, ordinary differential equations, sourced by density and pressure, you see here. But density and pressure are built in terms of the coarse-grained phase space density I've shown before for fermions, this F function here, and which is in terms of the integrated along the energy of the particles of the momentum, which is written generically in relativistic manner. This system is a boundary condition problem, which we will solve for regular solutions at the center. So the mass at the center is zero, so it's not singular. And we have three free parameters: the degeneracy at the center, we will choose a large than zero central degeneracies, the temperature, as you can see here, and the cutoff energy. Therefore, we have a system here of 4 free parameters with the particle mass, the temperature parameter beta, the degeneracy parameter theta, and the cutoff energy. So the challenge is here to understand which is the most general solution out of the system. And this was shown in this paper here in 2015 by solving the nonlinear system of coupled ordinary differential equations for boundary conditions consistent, for example, with a spiral halo, right? Because as we said before, the challenge to this theory is to try to understand the dark matter at on galaxy scales. So we choose a typical halo radius of 10 to the 4 parsec with a mass of 10 to 11 solar masses. And we can see that the outer part, it goes very well in this window of radius where data are available, are compatible with other profiles known in the literature as a NFW profile from the lambda CDM paradigm or a NASTO profiles. But towards the center, it develops a highly degenerate core, which is support against gravity by degeneracy pressure, and continuously transitions to a Boltzmannian regime, which is support against thermal pressure. Yeah, so we have these two physical regimes in the same system, nicely transitioning in a continuous manner, which do depend on the particle mass. And this is an important aspect of this theory, because we will see later on that the compacity of the central regions are sensitively dependent on the particle mass. So it is will allow us to constrain these values. Another important aspect is that it can demonstrate that for degeneracies larger than 10, the thermal de Broglie wavelength of the particles in the core are larger than the interparticle mean distance. So this is fulfilling the so-called quantum condition, or or Pauli statistics or Fermi Dirac statistics, and the profiles, as I said, depend on the particle mass. Now, the challenge will be to understand which is the role of this central core, because in the outer parts, the halo region is consistent with the profiles, but the core, we will see if which role can play on galaxy scales. So before moving to the phenomenology of this theory, let me talk a little bit about the stability and lifetime. This is important to mention that these systems, which I shown before, are solved for in hydrostatic equilibrium, some equilibrium solution. One can also demonstrate that they are stable and long-lived. What does it mean is that one should solve the problem of the second order variation of entropy when the system is formed. And this was solved in this work on galaxy scales for the first time, demonstrating that these core halo profiles are stable, so are maximum of entropy, and can calculate the typical lifetime of these solutions are also long-lived, longer than the age of the universe. So this allows us to consider this solution as a likely solutions to arise in cosmology. Besides, it's possible to find a critical point, a last stable solution, leading to a core collapse of this highly degenerate core, somewhat in analogy with what happened in neutron stars, but in this case, for system of finite temperature, where the central core can collapse to form a supermassive black hole. Therefore, now, once we have this typical generic solution in equilibrium and also stable, we can go to take a typical observations of a typical galaxy like the Milky Way, and do the phenomenology. We know the Milky Way is separated in the at first order in four components. The dark matter central object of 4 million solar masses at the center, presumably a black hole. The central bulge at first kiloparsec, the disk, flat disk at around 10 kiloparsec, and the outer halo, which is has a mass of typical 10 to 11 and 25 kiloparsec, and can extend at about 100 kiloparsec. And you see here in the bottom left the rotation curve, which shows the typical flat part in the right panel, but in the left panel we can see in logarithmic scale, which is joining the inner bulge regime, interestingly, from from typical few parsecs until the outer boundary. So we will use all this data plus the data of the S-stars cluster, which, as you may know, these clusters orbit the central object Sagittarius A star from around milliparsec scales up to parsecs. And the most important star here is the S2 star, which is the one best constraining the mass of the central object in 4.2 million of solar masses, within a pericenter of about 6 times 10 to the minus 4 parsec. So the first question here is, as you can already guess, is that we will try if these core halo profiles of fermions can this gravitational potential of the system can explain the Milky Way rotation curve as well as the S-star dynamics without introducing the black hole hypothesis. So we will like to model the central object mass with this highly degenerate concentration of fermions. So one can answer this formally by solving the system of equations shown before. We will choose the core mass of the fermions as the 4 million solar masses, and two typical halo scale values, one at 20 kiloparsec and the other in the outer boundary of the system given by the Sagittarius dwarf galaxy by Gibbons of the locule. And therefore, we have demonstrated that there is not only one solution able to reproduce this data, but it's a family of solutions which depends on the particle mass. Therefore, you can see here in the picture on the left, a family of density profiles. Yes?
Carlos, sorry for the interruption. You have 5 minutes to the 25, okay?
Good, thank you, Jorge. Yes, so we have a family of solutions that goes from 48 Kev and to 300, from black to dashed gray, where all these solutions are agree with the Milky Way rotation curve. You can see the fit in red here in the picture of the right. But all of these cores can explain the cinematics of this star because the core is compact enough to lay inside the pericenter of S2, and therefore providing an alternative to the supermassive black hole interpretation of our galaxy. The black solution is a solution above which the system, the core becomes critical and collapses, and for particle masses below 48 keV, the core is extended enough so that it overshoots the rotation curve. Well, for particle masses below 10 keV, it overshoots the rotation curve, and therefore this solution has to be excluded. These particle masses have to be excluded from this phenomenology. Well, this is assumed for the halo part of our galaxy, and I will show in the last minutes. I will end with the phenomenology we have done recently with our collaborators, Eduard Becerra, in this paper, nice paper of Eduard Becerra, and our colleagues, from the geodesic motion of S2 and G2 as a test of this dark matter nature. So in this paper, we took all the available data of BLT and the Keck 1-2 Gemini North Subaru telescope publicly available. And the point here is to reproduce not only the astrometry of the S2 star, but only the relativistic redshift, which has been detected 2 years ago by the gravity collaboration, 3 years ago. And yes, and also the G2 post-pericenter passage. So we can see here that S2 astrometry can be very well reproduced by our model with similar statistics, reduced chi-square as the black hole. We have also shown that the line of sight radial velocity can be very well reproduced as well, including the redshift excess. So this bump here in redshift, either in the black hole model in blue, and the RAR model, so for fermions in red. And then, well, I will just mention that the G2 object, which is not much well understood object, that has passed by, fly by Sagittarius A star. The astrometry can be well reproduced by the two model, but an interesting point, intriguing point, is that these G2 objects, the post-pericenter passage, these 3 dots, gray dots here, you see here, they cannot be well adjusted by the black hole hypothesis, the Schwarzschild black hole. And therefore, they in order to explain within the black hole paradigm, you have to assume friction within an accretion disk. And instead, in our model, the red solution, we can explain for the same particle mass of 56 keV, so the same particle mass that we use for the S2 star, we can explain the post-pericenter passage of this G2 object with very good accuracy. So this is a very interesting hint of this fermionic assumption. And finally, I will end here. We have finally reproduced, test this model with the 17 best resolved stars around Sagittarius star, showing that the dark matter concentration of fermions can explain very well all these orbits, similarly as the black hole paradigm. Thanks a lot, and I'm ready for questions.
Thank you, Carlos. You're perfectly on time. So we have time for questions, if any. So please, is any questions?
Jorge, could I ask question? It's Alexander Zakharov.
Of course, please.
I was enjoying your talk, and especially first part of your talk. But also, okay, I would like to know that when you consider your model for, let us say, dense core, in this case, this model originated, let us say, harmonic oscillator potential for galactic center. In this case, really, stars are moving along elliptical curves, but their center coincide with periapsis. So not with, let us say, foci, but with periapsis. So, but when you look at this picture, you see that it's let us say, your observational data do not confirm this claim that is moving along periapsis. It's the first part of my question. And second part, if you apply this model for galactic center or for M87. What about shadow for this case? Because in this case, you have dark matter, so there is no black hole. In this case, I do not expect the appearance of shadows. Thank you.
Yes, good. Thank you for these questions. So I will start from the second question. So yes, for these particle masses that I show here of around 50 keV, the concentration of fermions towards the center, let me go to these density profiles, are compact. So the compacity, for example, we can see this dashed gray solution. The radius is around 1,000 Schwarzschild radii respect to the black hole horizon, and therefore all these solutions will not cast a shadow, of course. So the point is, Alexander, that you can go to larger particle masses, and therefore the compact will be more and more compact until it will collapse to a black hole, and then of course will develop the shadow. Our claim is that it may be the case that for non-active galaxies like ours or others, there may not be supermassive black holes at the center. And but when you calculate the critical mass of collapse of a 50 keV particle mass, the critical mass of collapse, which is proportional to Planck mass cube over fermion mass square, it leads to a supermassive black hole of 10 to the 8 solar masses. So indeed, this is shown in another. So the critical mass for this system is 2 times 10 to the 8 solar masses. And so we are claiming that this may provide the seeds for formation of supermassive black hole in the early universe, and of course, including M87, which then should have to accrete on top of this seed. But this is an interesting alternative because it may help to understand why supermassive black hole can form in the high redshift universe, in the redshift 7 to 8 to 10, and grow so large so quickly, because in this case, as the galaxies are born core halo, this core can collapse and then provide this seed at high redshift. So this is the second question. And I think the first question, I don't know if you were referring to the periapsis precessions of these orbits, elliptical orbits. Alexander, I didn't understood perfect your question. Can you maybe repeat?
No, it's not a question about periapsis. So it's in principle, it's a question. Assume that you have without precession. We assume that you have spherical symmetrical distribution. And
Yes.
in your model, you have, let us say, ball with constant density. If it's a ball in constant density in the center of our galaxy or in center of your model, you have harmonic oscillator potential. Its harmonic oscillation potential caused elliptical curves. But the centers of these ellipses are center of force, center of periapsis. So it's in this case, that is let us say critical, let us say difference between Newtonian potential and harmonical oscillator. So yes. because in Newtonian potential, stars are moving around, let us say, focus, but in your model, they are moving around center. That is different. So it's because you see in your model, you have constant density in the center.
This is one important comment about this is that what you may seem at first glance constant, it is very important in our solution to consider the gradient of the density and corresponding in the gravitational potential due to the solution, because for example, the pericenter of the S2 star is somewhat outside that we call the core. The core in our solution is defined as the first maximum of the rotation curve. Therefore, where the central density core, the density has decreased from the very constant at the center, and so this gradient is important. So, it's not as simple as to say that you can model our solution with a constant density and then a halo, because the transition from quantum to classical is extremely important to make the phenomenology. Otherwise, you don't get the fits.
Okay.
Thank
but
you.
it's-
Thank you, Carlos. Thank you for your questions and your answers. But we have to stall where we will go out of time. So thanks, Carlos, for the presentation.
Okay.
So we can move to the second speaker. Is Hussein Hagi. Are you ready? Let me give you.
Stop sharing.
If you just make me presenter, I can share my screen.
Yes. Okay, you are now the
Okay.
presenter. So here we are. Okay, so we start when you like. Okay.
Yeah. Do you hear me well?
Yes.
Good. So let me just okay. Hello, everybody. And first, I would like to thank the organizing committee for inviting me to this talk. So in this presentation, I'm going to talk about the recently reported dark matter-free ultra-diffuse galaxies, which was reported by Peter van Takkum a couple of years ago, and that they claim that these types of galaxies are problematic for modified gravity theory like MOND. And I will show how the MOND simulations can explain the dynamics of these types of galaxies. Of course, I have already planned for a more technical talk in MOND, but as I saw in the last 2 days of meeting, most of the audience are not expert in this field. So I decided to start with a long introduction in dark matter problem and also its alternative like MOND. So this is the reason that why I added this subtitle here. So I start with a longer introduction actually. So this is the outline of my talk. My talk includes 3 parts. First, I briefly explain how the idea of dark matter was raised a few decades ago, and then I will address some of its challenges in different scales. Then I'm going to explain what the theory of MOND is about and how this works theoretically. Then I will give you a brief report on our recent analysis of ultra-diffuse galaxies. Specifically, this 3 guys, DF2, DF4, and DF44. The problem is that, in general, the problem is that in astronomical scales of larger than, for example, 1 kiloparsec, like stars in a galaxies or galaxies in a galaxy clusters, the objects move very faster than what we expect from the gravity of observed matter. So the idea is to reconcile this, galaxy scale observations. For example, for the first time, Suiki was the first one that showed the Doppler velocity of the galaxy in Coma cluster imply roughly a mass-to-light ratio of 400. And there are 2 different approaches that is suggested to explain this faster motion, either by adding some unseen mass or different law of gravity. I mean, the more gravity instead of more mass. So to give a general overview of, I wanted to begin by showing the problem that we are going to solve. And the problem is that if you plot the rotation curve of a galaxy as a function of distance from its center, then the data points are up here and show a flat rotation curve in the outer scale. But most of the galaxy mass is within 5 kiloparsec. So beyond that, you expect a Keplernian declining in the rotation curve. This is just what happens in solar, also in solar system, where the more distant planets orbit the sun slower. So of course, as you see, this is not correct for the galaxy. So what is the reason for this? One popular explanation is dark matter halo, which is distributed around the galaxy, around the visible part of the galaxy, that can boost the rotation curve because there is still significant amount of mass beyond the baryons, which is causing this boost to rotation curve. And the main point of this finding is that many galaxies with a wide range of different sort of galaxy masses and surface brightnesses have this flat rotation curve. So this is the business of the dark matter, the rotation curves. So in this picture, then galaxies look like this. So they have the visible sort of disk. Then there is this halo of dark matter, which is shown in black. But it is important to note that the real galaxies actually, the real galaxies that we see, just baryons. There is, of course, no direct evidence for this invisible mass. And all we have is the visible disk rotating too fast compared to the standard theory. So that is the flat rotation curve problem. And the problem, of course, is caused by the application of Newtonian gravity. It is an important issue. And it is because of the application of Newtonian gravity to the distribution of detectable mass. So this is, however, raises the issue of whether the Newtonian gravity is itself correct or not. The need for dark matter halo is also proposed by these guys to explain the stability of bar in some of these galaxies. In fact, the galaxies, the galaxy disks with bar, with this bar structures are unstable without extra mass. So we need, again, some kind of halo around the galaxies to have the stable bars. And another independent evidence for dark matter comes from the gravitational lensing of galaxies and galaxy clusters. And you see here the unlensed and lensed image of background galaxies. And the interesting thing is that the amount of matter to explain the lensed image is quite consistent with what we need for the dynamics of galaxies. And also in cosmological scale, we also need dark matter to explain the large scale structures and the distribution of the structures in the universe. Indeed, the non-baryonic matter is needed to collapse earlier than the baryonic matter to form structure formation, the structure that we observe today. So yeah, we need dark matter also to explain the matter density fluctuation that we see in the cosmic microwave background radiation. And so in general, I mean, if I want to summarize, according to the standard model of cosmology, the universe basically starts with a Big Bang and a hot plasma, and we also have inflation period, and the universe expands, and today we are experiencing again a new inflationary period because of the action of dark energy. And as the universe expands, the gas cools, and the first stars and small galaxies are formed and merge to form larger galaxies. And today we would be observing the universe and these galaxies. So yeah, in the standard model of cosmology, we need dark matter particles, and of course that are not the part of the standard model of particle physics. And we need dark energy, which is totally not understood. And also we need dark baryons, and we need dark forces, and we need inflation and some sort of fine-tuning of galaxy formation of cosmological simulations. So an important fact is that the dark matter particle still not observed despite the decades of very expensive experiments. And the dark matter hypothesis also faces very serious problems in small scales, I mean galactic scales. Here I listed some of them, but I would just briefly explain part of this list in my presentation because I don't have enough time actually. So one of these challenges is the distribution of dark matter in the center of galaxies, known as the core cost challenge or core cost problem. In fact, the dark matter only lambda CDM simulation, the halos are too costly at small radii compared to many observed galaxies. Indeed, the observed galaxy rotation curve don't follow the theoretical prediction from cosmological simulations. And so, for example, in this case, you can see in low mass or low surface brightness galaxies like this one, DDO 126, which has a well-measured rotation curves. The rotation curve shows a better fit with constant density cores at the small radii instead of the Cosby profile, for example. So to solve this problem, some solution is suggested mostly based on the effect of baryonic physics. It seems the feedback process, such as stellar wind, supernova outflow, can reduce the central density. But most of this solution works only in a range of galaxy mass. And for example, for low mass dwarf galaxies and for very high mass spirals, it doesn't work as far as I know. Now, let's see what happens in cosmological scales. They are two clusters which have collided each other and gone out again and left the gas in between, this red part. In bullet clusters, there is an offset between the X-ray, the gas distribution, and gravitating mass, which is shown here in blue, as obtained from Wick lensing. And it was argued to be a strong evidence for the existence of collisionless matter. So one important aspect of bullet cluster that was considered as a problematic is the high collision velocity. Actually, the observed velocity of galaxy cluster that is predicted to be the order of 200 kilometers per second in the CDM model, but from observation, it should be about 3,000 kilometers per second, which is too higher than expected from lambda CDM simulation. So this is a serious problem for cosmological simulation. So another challenge that I would like to address is the phase space correlation of satellite system around the galaxies. We can observe the three-dimension distribution of satellites, or better, I would say 6-dimension, because we have also the data for velocity of the satellite. So this is the picture of satellite galaxy around the Milky Way, for example. And this is what we see from observation, from cosmological simulation. Each point here is a galaxy which is orbiting around the main galaxy, the most massive galaxy in the center. And it is found in 2005 that the satellite galaxies are in a plane much like the planet around the sun. And so the question is that, is the Milky Way unique in this regard or not? And the answer is no, because the similar plane of satellite is seen in the nearby galaxy M31. And the question again is, how about the other galaxies? And for example, the Centaurus A, which is a very close group to our galaxy, it has also a large population of satellite galaxies, which is in a thin plane, which is rotating. So this proves that the Milky Way and M31 planes are not unique. And in fact, these are 3 cases. So Milky Way, Andromeda, and Centaurus A, that are the only that we know the 3D distribution. So for these 3 cases that we have the accurate data, we see all of them shows a plane of satellites. So it seems it is a rule and not just an exception. And combining the probability of such system shows a 5 sigma falsification of the dark matter models. And another important challenge is the shape of the galaxy, the morphology of galaxies. And the shape of galaxies that we observe today is inconsistent with what is expected from lambda CDM simulations. For example, in simulations, less than 10% end up in a disk form, but in observation, we see about 90% of galaxies in the form of disk. So it is a very serious challenge for lambda CDM. So yeah, after addressing these problems with lambda CDM, now we are motivated to see the alternative to dark matter. So one of the most successful alternatives to dark matter is MOND, Modified Newtonian Dynamics. It was developed by Milgrom to address the rotation curves in 1983. By the way, only a very limited amount of data was available in 1983, and just a few high surface brightness galaxies. So similar to the Newtonian, Newton being motivated by moon's motion, for example. The prediction of rotation curves for low surface brightness galaxies were successfully approved much later. I think it's about 1990 or 2000, I don't remember exactly. You can write a Lagrangian for MOND. One to understand is that the kinetic part of the action, this part, is not modified, which means we have standard law of inertia. And the gravitational part, this part, is modified to get this Poisson equation, this modified Poisson equation. And because this new Poisson equation is nonlinear, it breaks the strong equivalence principle. And there have some studies which actually found the strong evidence for this. So this nonlinearity makes the use of the usual Newtonian embodied simulation codes impossible in MOND regime. As a result, the internal acceleration, as a result of nonlinearity, the internal acceleration of a system with mass distribution depends on the position of another objects or host system. For example, the internal velocity dispersion of a globular cluster or dwarf galaxy depends on the gravitational potential which is induced by host galaxy, even if the external field is constant. And so this is a unique effect that we don't have any counterpart in Newtonian model, in Newtonian gravity. So according to this effect in MOND, the internal gravitation of a bound system is suppressed here. Yeah, and by an existing external field, if it is sufficiently strong, a dwarf galaxy has weaker self-gravity when, for example, if it is in close proximity of massive hosts. So in a simple word, the external field reduces the strength of the gravitational acceleration in a system, for example. So as I said, this effect is completely unique in MOND and doesn't exist in a standard gravitational model. So it makes an important prediction for MOND and important test for MOND. And for example, in this research paper, we studied the rotation curves of a sample of spiral galaxies and showed that the external field can successfully remedy the overestimation of rotation curves in galaxies in MOND fields by decreasing the velocity in the outer part. So as I said, the external field can decrease the velocity in the outer part of the galaxy. So you see, we get a better fit if we assume the external field. And interestingly is that the amount of external field is consistent with the amount of acceleration that this galaxy, for example, experienced from the nearby galaxies. So now let's see what is the... Yeah?
Sorry, I have 5 minutes left.
Okay, that's fine. So now let's see what is the prediction of MOND for the internal dynamics of spherical system. Here, let me just skip this slide. I think because, yeah, it's better to go to this slide. And yeah, in 2009, when I was about finishing my PhD, I calculated grids of M-body model using N-body code, which is a code developed by an Italian group in Bologna, to formulate the internal velocity dispersion of a spherical system in the intermediate region. And I found an analytical formulation for velocity for velocity dispersion as a function of external field and internal field based on the Mondian embodied simulation. So for any, so you can see here, for example, the velocity dispersion of a system in general as a function of external field in this form. So for any non-isolated system with non-external acceleration, it is possible to calculate the velocity dispersion using my formulation. And so it is important to apply this formulation for example, dwarf galaxies in a galaxy clusters. So then we apply this formulation to calculate the internal velocity dispersion of ultra-diffuse galaxies. But first, let's see what is the ultra-diffuse galaxies. Actually, a fundamental prediction of hierarchical galaxy formation models is that all galaxies are surrounded by a vast of complex network of ultra-low surface brightness filaments and S-streams, which is a result of high merger rates of the halos. So search for galaxies with low baryons content is very difficult outside the local group due to the low surface brightness. And the Dragonfly telescope array was designed by Peter van Dokkum a decade ago to probe the universe down to the very low surface level. And because their lenses have no light scattering, they can reliably get image down to 32 magnitude. That's 40 times fainter than current telescope in the world. And so they found a new class of ultra-diffuse galaxies in 2015. And since then, about 1,000 of such galaxies are discovered. So you see their typical size is about 2-3 kiloparsec, similar to the Milky Way size, but the mass is about 10 to the minus 3 times lower than the Milky Way mass. So for that reason, these systems are extremely diffuse and low acceleration system, which is a Mondian system, I mean. So here also you can see the NGC 1052 DF2, which is in size similar to the Milky Way almost, but in mass is very smaller. And for that, the velocity of this galaxy is extremely smaller than the Milky Way. It's about 7 kilometers per second compared to 200 kilometers per second. So yeah, here is some figures of this field. This is the Dragonfly field. NGC 1052 is this. And if zoom in, you can see DF2 and some other galaxies in nearby. So yeah, we try to explain the dynamics of these two objects. Yeah, let me, because of time limitation, I skip the details. Yeah, let me just show you the stellar mass. It's important to see that the stellar mass of the main galaxy, NGC 1052, is about 10 to the 11 solar mass, and the separation is about 80 kiloparsec from DF2. So we show that the external field effect of this galaxy is important for that dwarfs. And in the first report by Van Duckom, which was published in Nature, they reported a galaxy lacking dark matter. They didn't assume the external field of this main galaxy. So they found a wrong result, that the dynamical mass to stellar mass is about 1.7. So they claim that it seems that the dynamical mass of the system is similar to the stellar mass, which means that this galaxy doesn't have any dark matter. So we wrote a BCA in Nature in this regard and showed that the claim is wrong, and there are several problems with their results and conclusions because they didn't consider the external field and ignored this very important effect of MOND. Since they didn't find, I mean, they claim that this galaxy is without dark matter, it makes a serious problem for modified gravity models like MOND, because in MOND, these systems are completely Mondian system, low acceleration, and we expect more gravity in the system, which is in effective way, we expect more dark matter actually. So in this PCA, we showed that the external field effect can play a role for these guys, and show that the dynamic, let me skip the details. Just you can see here that the velocity dispersion of this system as a function of the separation, because we don't know exactly what is the separation of DF2 from the main galaxy. We just see the projection. So actually, this is the minimum distance of these two guys. So if we change the distance, even for a very larger distance, we show that the velocity dispersion is consistent with MOND in 1 sigma level. And also we did some n-body simulation, and yeah, and just 1 year later, Van Duckom reported the discovery of DF4 as a second galaxy lacking dark matter with very similar properties to DF2 in terms of its size and surface brightness and morphology, and distance, of course, with the velocity dispersion of about 4 kilometers per second. Again, for this case, we showed that these three main galaxies, which are listed here, NGC, I mean, yeah, the DF4 is near to these three galaxies, NGC 1035, 1042, and 1052, assuming the external field effect of these galaxies can reduce the velocity dispersion of this galaxy to be consistent with the observed value. So again, we showed that these systems are consistent with MOND. So yeah, I would stop here with my conclusion. Actually, we provide analytic formulation to take the external field effect into account to estimate the dynamical mass of non-isolated system. And we showed that the dynamics of DF2 and DF4 is pretty consistent with MOND prediction. And yeah, that's it. Thank you.
Thank you. Thank you. So maybe we have time for one short question and short answer. If there is any question.
Could I ask a question, Jorge?
Please.
I remember that when, let us say, people discovered bullet cluster and claimed that is direct evidence for dark matter, MOND people said that they could fit observational data with MOND theory, but they introduce neutrino mass around 2 eV. What about recent progress in this direction? I mean, to fit observational data for bullet cluster with MOND. Because it looks very heavy, neutrino mass. 2 eV is too much now.
Yeah, exactly. Yeah. Yeah, in 2007, I think Gary Angosh in St. Andrew, I mean, in a research paper showed that the stereo neutrino can reconcile the bullet cluster with MOND. And recently, in other case, El Gordo, Elena Asensio and Indranil Banik and Pavel Krupa and University of Bonn, they showed also that the El Gordo case is also compatible with MOND if we introduce the neutrino, stereo neutrino as a collisionless matter, which is, I mean, not assumed to be dark matter, of course. It's a completely normal particle that we expect in standard model of particle physics. Yeah, of course, without stereo neutrino, it is difficult to explain this observation in MOND.
Thank you, Haghi. So thank you again for your presentation, and so we can move to the next speaker that I see already. Hi, Clement. Hi, Clement.
Question out of my talking time.
Sorry?
Can I borrow 30 seconds of my time to ask a question?
Yes. Okay. Okay.
Okay. Yeah. So thank you, Hussein, for the presentation. You say your analytical estimates that you derived during your PhD are spherical. You know, you have the spherical symmetry approximation, but as far as I know, most of galaxies are not spherical. So isn't it a spherical problem, or do you have you know, correction to the sphericity, or where do you stand here?
Yeah, on that time, it was the only way that one can assume the external field effect. And I used that formulation just for a spherical system, like globular clusters and dwarf spheroidal galaxies. It is not possible to use that formulation for example, a spiral galaxy. But now we have some M-body simulation code like Quantum of Ramses that can do a realistic simulation and implement the external field effect for this.
And Quantum of Ramses agrees, I guess, with your analytical estimate.
Yeah.
Very well. Thanks. Good, then I just had time to set up in the meantime. Should I start, Jorge?
Yes,
Right?
you can start, please. Please go ahead when you're ready. Okay.
Well, so thank you for the invitation. Welcome to my talk. Yeah, I'm Clement. I did my PhD 4 years ago, I think, with Professor Remo Ruffini, back in the time in Pescara. And in the meanwhile, I moved more to field of large-scale structure. And so Roche asked me to review a bit what's going on there and what we are doing. So I think I will follow a bit the same strategy as Hosein. And it's also good because he introduced a lot of concepts that I have no time to introduce, but I would have been willing. And we do a really long introduction, given the audience, on large-scale structure and especially cosmology. So most of the people in this session, I think they also talk a bit about lambda CDM model, but more from the galactic point of view, so on the smaller scale. And here what I want to tell you about is more on larger scale. So I will speak about what we mean by cosmology, what are the larger scales and so on, and linear structure formation. Then I try to tell you a bit of chosen techniques, how to go beyond linear regime, both from analytical point of view and also some mind-body simulation, at least give you a flavor, hopefully show you a movie if I can share my screen. And and then if I have some more time, I tell you 3 little projects I've been currently working and where do I stand, in this whole community. And the 3 little projects, I link them because in 3 of them, I didn't study Poisson equation, Newtonian physics, in order to describe, matter interaction, gravity interaction on the larger scale, but I did something else than Poisson, going beyond Poisson. And I'm also currently interested in MOND, as Hosein was discussing, and I found the external field effect, so beyond lambda CDM also, with the second project with 2 Poisson equations. Very well. Okay, let's get started. So, one slide, cartoon slide to tell you where we stand. So cosmology, the goal is to study on the larger scale. So galaxies, okay, most of the time you make statements for kiloparsec scales and so on, 100 of kiloparsec maybe. But in cosmology, you really want to zoom out and to go to megaparsec, maybe even gigaparsec if you are fit. And all those scales, the probabilities are different. The universe, you have more symmetries and so on. The universe is almost homogeneous, isotropic. And you can look at the larger structure if you want to do large-scale structure, cluster of galaxies, filament, voids, and so on. Okay, on this cartoon, time go from left to right. Okay, can you see my mouse? I hope yes, otherwise not very important. And one of the questions one can ask in cosmology is how to start, say, from a very homogeneous and isotropic universe, and how to form all those galaxies, cluster of galaxies, and so on. And that's the field of large-scale structure. Large-scale structure is trying to answer this question. You start with initial condition coming from very early universe, and you go all the way to cluster of galaxies, the diversity of structure we see today. And technically, is nothing but fluid mechanics in an expanding universe. So since you're on such large scales, you can approximate the matter content with different fluids, perfect fluids, which have a density, given density, pressure, and so on. And, and you try to look for them. So, yeah. So in this field also, you have this important split, I guess you heard of it before, between background quantity. You can make background statement. The universe is expanding, how is it expanding, what is its content, how many neutrinos, and so on. So all this, if you talk about dark energy, accelerated expansion, these are background statements. So they can be done with background probes, like supernova, big nucleosynthesis, nucleosynthesis, BAO. And on the top of those on the top of this background, you have little fluctuation. Okay, we are one of the fluctuation, and all the structures are meant to form on the top of this background. And if you are early enough in time and on large enough scale, this background, is a Friedman Robertson metric, isotropic and homogeneous. And you try to construct after this the little perturbation, which obviously grows to be small. Here we are in a big, or obviously grows to be big, sorry. We are in a big perturbation, And as I said, you have a bunch of assumptions in order to get something done. So, linear fluid mechanics, we start like this. And also assume that we have Newtonian equation. So, we are not nearby black hole. The velocities of the objects we are looking are small, 10 to minus 2. And, we are not near seeing the cosmological horizon, local Newtonian physics. And if you do that, you can derive quickly if you take Boltzmann equation, Poisson equation. And if you do all the simplification of assumption, you end up with this famous equation, which I wrote a cartoon-like here, which, tells you that the density contrast, a bit like in the stars, it is a constant fight between the expansion of the universe and gravity. So, if you're under the right condition, you can have gravitational collapse and you start to form structure and so on. So that's the bottom line. And then, you have to work out the details, know the gravitational potential of the universe and so on. And but, that's possible. You impose initial condition. But, the initial condition, we don't know them very well because we only have one universe. So you cannot do again the experiment and infer the initial condition. So the initial conditions are statistical, we can know the statistical property of the initial condition. And therefore, if we want to look at large-scale structure, we also need to look at statistics. So, okay, what to look for statistics? If you take average, you put it back to the equation on the top right here, and you find that the average of delta is 0 by construction, so not very useful. So the first thing you could think about would be the variance. And I suggest not to take just the variance, but to take the 2-point correlation function. If you put x equal to y, you get back the variance, but you have more information. And it turns out it's already pretty useful because on the larger scale, your universe looks almost Gaussian, And from your statistic class that a Gaussian field is described by only one number, which is the dispersion and all the 2-point correlation function. So if the universe was Gaussian, for use Wick's theorem, you have all the information with P, and the structure that form and some they induce non-Gaussianities, in some controlled way you can see. So if you want to see beyond Gaussianities, you need to go for higher order correlation, which are pretty useful also. But most of the data analysis they do with the this power spectrum, and you already have a huge amount of information there. Good. Okay, moving on. So I just want to tell you a little bit about observation. So I choose this one, many observations. So this is the power spectrum I was telling you, and this is a compilation of many observations we have. So, okay, from CMB on the larger scale. So it's in Fourier space. So left part is the larger scale, and the right part is the smaller scale. And you have various probes like cosmic shear, luminous red giant galaxies, Lyman alpha, and so on. And okay, they look all to stand good with respect to the black line, which is a theoretical prediction. But I cheat you a bit because what I show you so far is a linear solution, and the linear is a dotted line. So it's not fitting on the smaller scales, okay, obviously, because as I told you, it's a non-linear structure formation process. But on the larger scale, linear physics is enough. And yeah, didn't do my homework, I didn't connect one day in advance, so I don't know if I can show you a video which show you some linear observable on BAO, so I try to click. So do you still see, somebody sees my video?
No, we see your slide.
You still see the slide?
Of the power
Okay, I
spectrum.
try 2 seconds to show you the video, otherwise we skip. So what if I show you? Yes, maybe I'm succeeding. And now you see, right?
Yes, we see you
Super.
too.
Okay.
Okay.
Perfect. Okay. So those are some linear effects. So it's this so-called BAO, and those can be seen in observable, and this will give you a flavor also of what is the power spectrum in cosmology if you didn't encounter it before. Yeah, I told you it's a long introduction. So you see those little BAOs, they make some pattern beyond the homogeneity scale, some extra over densities, little over densities. And and these little over densities, you can have stars on them and so on. On the top of them, you can put your structure. And in principle, you have more structure when you have more over densities, right? And this can be observed then in principle. So this video was not made by me, obviously. And but this is collaboration Castro, and now they show you all they measure. So it's not power spectrum, it's 2-point correlation function. But I told you, 2-point correlation function is in Dirac space, and power spectrum is in Fourier space. So here they really take the spatial distance between 2 stars that they observe, and and they look at the frequency of the stars they do, and they do it for many, 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 and in order to have good statistical measurement. And at the end of the day, they get nice measurements. And this little bump here is the BAO peak. Okay, that's more or less what I wanted to show you. So, so in order to measure power spectrum, that's what you do, You look at a lot of stars and you try to measure them. Okay, so I guess now I know the procedure to share again, go back to the slide. Okay, very well. Okay, if I am quick enough, I can show you more video. Otherwise, we do more calculation and stuff. Very well. Okay, so let's move beyond linear regime. And in order to do so, okay, so you have this linear solution, which is valid at large enough scale, and then you want to go nonlinear, to go to more in time and to go to smaller scale. And yeah, as I show you on previous picture, you fail big time, starting from 0.1 in a megaparsec here. So at those scale, you need something more. And what you can do is to push by calculating in powers of the linear solution. So here I just wrote an expansion, delta is delta 1 plus delta 2 plus delta 3. And delta 2, I take it as a power, a square of the linear function, multiplied by some kernel which remain to be calculated. And those techniques, they have a diagrammatic interpretation. If you know a bit, from Feynman diagram, okay, those are called weak diagram because it's not quantum. But, you have a diagrammatic interpretation. But the goal is to calculate those Fn, And then when you have the Fn, you can calculate correction to the power spectrum called loop correction. And it's called loop because there are loops in the diagram. And okay, you have a formula, a recursive formula for Fn that you can find in this review, and you can derive. It's not very hard. You can see how it derive in the review. But once you have those Fn, you also remain to calculate all those convolution integrals, So it's still a bit costly, but you have some techniques. And I did it for you at one loop. And so the blue is the previous linear power spectrum, and the yellow is the correction, And you see that starting to 0.2, 0.2, 0.3, this correction start to kick in, is important, and it rests your power spectrum. So this helps a bit, you can go all the way to 0.2 maybe if you are lucky. But, it's not enough, and this you can do really quick. In 1 hour, you can do this calculation. So, in the past 30 years, people did more than 1 hour calculation. So you have a lot of techniques imported also from high energy physics, since it's Feynman diagram and so on. All the people from QFT came and try to regularize some of this perturbation theory, try to, apply a lot of techniques with various success, and could push a bit to 0.3, 0.4, Obviously, you cannot go all the way to galaxies, because it's a simple approximation and so on. But, it's nice to have theoretical prediction. So I wrote a little review about them, so I put you here if you want to see the reference, if you're excited of one of them, if you know. And I want to speak a bit, but I don't know how I'm doing this time. Yes, yeah, I will speak about that. That's more interesting. So, yeah, so one of those techniques I want to tell you is this effective field theory. And in that case, they put a cutoff scale on a small scale cutoff, and all the physics above this cutoff, they don't try to measure, and they integrate it out, which is a QFT procedure, in order to get effective viscosities and speed of sound. And those parameters are not predicted by their theory, and have to be measured in some n-body simulation or, jointly measured when you do to data. And here they show, and here, once they fix these parameters, they can push their perturbation theory all the way to 0.3 here. So they are really happy. And with that, they look at data and got some nice constraints, So it's not amazing already. So it's the green big one, So it's not as good as Planck measurement and so on. But the claim is in large scale structure is not the end of the story. Planck is already exquisite measurement, and there is no more satellite plan to measure against it in Planck. But here, there are many more probes which will decrease this alone green line. And if they put Planck plus their own green, it is a small green ellipse, so it's quite good. They claim no tension. And that's one example. There are many more groups doing other techniques than effective field theory. Those guys do RED-PT, those guys do Bayesian inference, and so on. So you have many ways to do. And it's really exciting because in principle, in the 10 years, there will be many satellites giving better data than those BOSS, which are already a bit old, like 5 years ago. Very good. So that's the bottom line. It's very good data. I try to go a bit faster now with some slides maybe, because I see time passing by. And I want to show you more videos because it's fun. So, okay, just to say that in the future, there will be much more telescope. I list some of them. And it will be really exciting, shrinking the ellipses when people do data analysis. And okay, the money is already on the table for some of these experiments. I skipped that one talking about SphereX. But okay, it's just an example of experiment saying it will be really amazing. That's the bottom line, not only for cosmology, also for galaxy and so on. And what remains to be done, to my view, is to improve the theory modeling, both from analytical techniques and from numerical point of view, and to improve the data analysis pipeline, because the observer will be already amazing. And let me tell you a bit about n-body simulation, because that's my current main area of research. And those theory I show you, is not complete. It's effective. It's all the way to some small scale. You cannot resolve all the small scale with those theories. It's not too complicated, unless if you make some simplification. So people rely also not only on theory and don't throw away all the rest of the data, all the galaxy and so on, but they try also to do n-body simulation. And that's more or less what I've been doing. And the state of the art, to understand large-scale structure, the black line I was showing you a bunch of slides ago, comes from n-body simulation, this black line here. So complemented by analytical calculation. So it's worth to take a look to this n-body simulation because it's state of the art here, Okay, let me try to tell you a bit about my research during the 8 minutes which remains. So, okay, the first modification to this, so I try to modify Poisson equation because, one wants to go beyond what I've been showing you so far. And one wants to try to test GR on the larger scale, to see if really, Poisson equation is enough. Do you need GR? Do you need to go beyond general relativity on those scales which are not well tested? And so I moved from Poisson equation number 3 to this more complicated equation. And why did I do that? Why I was crazy, to do such a complicated equation? I don't want to go into all the detail of the term, but it stems from general relativistic metric compatible with Friedman equation and with perturbation pushed, to second order. So those perturbation, you have perturbation not only in the matter sector, but also in the gravity sector. So I did this ADM and I perturbate, I got 5 psi, 2 gravitational potential, also the vector, and gravity has usually in GR formulation 6 degrees of freedom. 2 scalar, 2 vector, 2 tensor. So you want to study those other degree of freedom in order to constrain GR, and not only if you do Newton physics, you will only probe this phi. So you have various motivation to do that. I'm not the only one to do. So on future survey, it will not be enough to do Newton physics because we will see scales close to the horizon scale. Therefore, we'll feel the GR, and it's exciting, to feel GR because you can see also dark energy and so on. And you can excite those relative degree of freedom and constrain them, as I saw, the vector tensor. You can model in such a framework all those relativistic species, which Newton physics is still tricky how to model them. So I list some of them: interacting dark energy, cosmic strings, and so on. You can model them in this framework. Okay, this is back reaction. If you have questions, I can say more. I want to go faster. And at the end of the day, you observe on relativistic light cone. So why not work in a GR framework? Okay, and what I realized also, so I tried to do calculation, analytical calculation, push, calculate F2, F3, F4, with the formalism I was showing you before, to calculate the nonlinear relativistic correction. And what I found with 2 of my students back in Chile is that those relativistic effects at the level of the bispectrum, so in nonlinear physics, at the 3-point correction function, they are totally degenerated with some subtle primordial physics effect, primordial non-Gaussianities. So I want you to look at the red and the yellow line, which is the line I calculate. And I put on the top of this another line, the purple, and the purple I put it equal to, so it's some primordial non-Gaussianities effect, and I put it equal to 1. But it's proportional, so I can put it to any value, and by choosing to find FNL, it's 10 to minus 1, I can find the yellow line, and if I put it 100, I find the red line. So in principle, it's totally degenerated, and it's a bit annoying, because the future surveys, they want to see those subtle primordial non-Gaussianities. So I will skip also this slide. So this is what, just to say in a few words, that these primordial non-Gaussianities, they are quite useful if you want to know about primordial physics. And you have a prediction from different primordial physics models, different inflation, which give different value of this FNL, which is this parameter controlling the primordial non-Gaussianities. And I studied some model which predicts some amount of non-Gaussian also with Hosein. So I don't know if it's here, maybe you remember we did this calculation with Stringer effect, was fun. So in principle, this can be proud in future large-scale structure, but one needs to do carefully the job. So okay, just quickly this I can tell you. So by Gaussian, I mean just the log of the probability of a fluctuation is like this. And if you have, other theories, the one we study with Hosein, for instance, they predict other patterns for the fluctuation. Good. I also implement this equation in a code, embody code, called G-evolution, and I implemented a bit in order to back up my analytical calculation with state-of-the-art embody simulation. And we put the paper out with the main developer of this code and my PhD student a couple of weeks ago. And we are the first one to calculate a B spectrum in a relativistic embody simulation. And again, we found that the GR correction are totally degenerated with primordial non-Gaussianities. And in the future, I would like to shoot ray in this simulation we did. It exists already within G-evolution, but I want to do it in order to include the travel of photons in this embody simulation. And in principle, then we can compare with observation. So it's quite exciting. Good. Another project, quickly flashing what I did, is I consider this so-called Dirac mean universe. I did that this year in Paris with some people. And instead of having one Poisson equation, one has two. And okay, that's more or less all I want to say because I see my time running out. If you ask me a question or if the next speaker borrows some time of his talk. So yeah, I have two Poisson equations. I modified the embody code in order to have two Poisson equations and try to test it a lot to see whether it's good. And I found some interesting thing also echoing the previous talk. So I found also this external field effect. I look at scaling relation at Tully Fisher, and I also give some hint when the radial acceleration relation, also from MOND, might be explained in this model. And you have a bunch of prediction from my model here. So first, the acceleration scale of MOL is redshift dependent. And second, you have much more small scale structure at high redshift. And third, this model, I didn't go too much into the details. There is no dark energy and no dark matter in this model, but you have anti-gravity. So it's a bit crazy, but it's currently being tested, in the next months at CERN. So I have my GitHub package, so if you want to check it out. And I think I have 2 more minutes. So if you accept, I show you a last project during 1 minute, and then and then a little movie of 20 seconds about this second project. But I prefer first to show you because it's a mess when I change. So yeah, the last project I'm currently doing in Strasbourg with some collaborator. I'm modifying again the embody codes to take into account a new Poisson equation with a new term also. And this term is in analogy with electromagnetism. It's polarization gravity. So it's also speculative, pretty speculative. It was theoretically developed in Paris by Luc Blanchet 10 years ago. And we tried to implement it in embody simulation and to look at the stability of galaxies, also maybe this Tully-Fisher, relation. And hopefully, if the code starts to work at some point, which is not the case yet, we try to run a cosmological embody simulation. Good. So just to sum up, those are the 3 Poisson equation upgrade I did. Many more on the market. I list some of them here. I guess I can share my slide. You can read them, study at home. And yeah, I try to show you a bunch of cosmology. It's exciting time for cosmology those days, with tension, dark species, and so on. So stay tuned. And I wanted to say thank you for your attention, but I try also quickly to show you one movie I did. It's a 20-second movie. I think I am on time, so I can do that. And I try to do it. So yeah, it's always a mess. Give me a sec. Yes. Yes, you see. Do you see?
Yes.
Super. Okay. So just 20 seconds telling you. So I run it. It's an embody simulation with 2 species. So it's the second project I was showing you, 2 Poisson equations. So there is the red species and the blue species. and I start from, you know, homogeneous patch, and the red species and blue species don't respond same to gravity. So the red is spreading all around. It's never collapsing because it's a, you know, repulsive gravity, you know, so it's negative mass and so on. And the blue is standard matter, so it can accrete, it can get attracted to itself, you know, and it accrete to form the standard galaxy. So that's actually how you form the external field effect, you know, because the red add an extra force to the blue to push it so that it feels more gravity. And that's how you can escape and not having dark matter and just baryon, a bit à la MOND. And we found things similar à la MOND. And then maybe that's all I want to tell you because I see my time is past. So yeah, I stop here. Thank you for your attention.
Thank you, Clement. Yes, maybe we have time for more short questions. Let's see. There is any question for Clement?
May I ask my question?
Please,
Yes, sir.
Hussein. Go.
Yeah,
Okay.
thank you very much.
First of all,
Your interesting talk. You said that you found a functional form for A0 as a function of redshift, yes?
Yes, we did.
And how is it the functional form? I'm interested to see if it is similar to H0 functional form or it's different.
Well, okay, you caught me off guard. I don't have backup slide. I usually have a lot, but I did that last night. So what I can tell you is that it's increasing with respect to time. It's not analytical functional. Oh, maybe, okay. If I open my paper, I can show you the plot. Usually I would have one in the slide, but I open the paper and I show you the plot. That's the simplest. Then you can see as a function of redshift, you know, the A0. Okay, so I need to share again some other screen. Hopefully I succeed. Now I'm expert in sharing my various screens. Yes, super. Okay, so it's at the end. Sorry, I'm also. You are seeing, right? The archive.
It is on archive, this paper? Or
Yes, well, it's published in ANA, but yeah, you can find it on archive. I put the reference also in the slide.
Okay, thank you.
Yeah. So this is it, figure number 15. I don't know how we end up having so many figures. So this is scale factor. This is here today. We don't recover exactly. A0 is 1.2 10 to minus 10.
Mm-hmm.
And you see that it increased with redshift, and this is like one redshift 100, you know, scale factor. So it's bigger, you know. So
yes, exactly.
In principle, you know, this I guess can be tested with hopefully future rotation curves at higher redshift and so on.
Yeah.
If you are more ready to test it, I'm more than.
The scale, it is almost linear, at least for.
Well, this is log scale, so it's power law.
Yeah, in log scale. Yeah. Thank you very much.
Yeah, welcome.
Thank you, Clement. Thank you.
Okay, may I also ask a question?
Please,
Yes,
short question, short answer.
Okay, I'll try to keep it short. First of all, thank you for your talk. You talked about your work on modification of Poisson equation. Could you please elaborate a bit more about why do we need to modify these equations? Why do we feel the need to go and modify them?
Yeah, so I don't feel any need. I can sleep at night with the Poisson equation. I'm more than fine with that. So that's for number 2 and number 3, you know. So some people tell you, yeah, dark matter, dark energy, and so on. I'm agnostic about that. It's just that I find it fun to modify the body code. For the first one, I can tell you that I need to modify it because I want to look at those effects. And I don't know if I have a backup slide about that. I want to look at those effects which mix. No, I don't. I want to look at those effects which mix large scale and small scales. Therefore, my correlation when I will look at the bispectrum or at the power spectrum, or those things here, when I will look at the bispectrum and the power spectrum, I will probe horizon scale. Therefore, my physics will not be Newtonian. I will feel the cosmological space-time, the fact that there is a cosmological horizon and so on. And this, I think it's, you know, well tested and so on. And my survey in the future data, they will probe those scales. And they will look at correlation between large scale and small scale, or large scale correlation. And in those cases, I do feel the need to go beyond Poisson, because, you know, the best theory of gravity we have is GR, and not Newtonian physics. Was it short enough, Jorge?
Yes.
Yeah, thank you.
Thank you, Clement. Thank you very much. So we are a bit late, but let's see if we can recover. So please, let's move to our last speaker, which is Professor Alexander Zakharov. I don't know if he's already okay. I think you can share already your screen.
Okay. Could I start? Jorge, could I start?
Yes, you can start. You can share your screen. We don't see your screen yet.
Okay, you don't see?
No.
Okay.
We see your face.
Okay.
We see
It's going
you,
to appear in a few seconds.
Okay. In this case, I will repeat procedure, but it's not allowed to share my screen. Something is wrong. Okay. Do you see my screen now?
No, not yet.
Okay. I don't know what is happening. I will try to share, but it's forbidden to share my screen.
I don't know what's happening. We have given to you the power to do that.
Okay, but it's...
Actually, we gave already the permission to him,
Yes.
Jorge.
Yes, I know. I see it here.
Yes, but it's forbidden. I don't know why. To share my screen.
Okay. No, what is not happening? Did you see that?
We have
Alexander.
we have given to you the okay, now here we are.
And now do you see my screen?
Yes, please proceed.
Okay, thank you very much. It's first of all, I would like to thank organizers for this nice opportunity to present this talk here. It's do you see my second slide or not?
Yes, we see it.
Yes, we see
It's
everything.
2 years ago, Event Horizon Telescope team presented shadow around the center of M87 galaxy. It looks like really logo for black holes. So you could see that many newspapers, journals publish this paper, and also its key references, outline of my talk. There are 3 basic pillars for M87 with star picture: synchrotron emission, VLBI observations, and black hole geometry, or JR in strong gravitational field. So, you know, as any success, it has many fathers. And one of the first person who considered synchrotron emission was George Schott, because he published a book more than 100 years ago where he considered synchrotron emission. But in 40s, synchrotron emission was rediscovered in Pomeranchuk and his co-authors. And soon after that, Elder and others found synchrotron emission from electron in synchrotrons. And so, but 2 first people who suggested to use synchrotron emission in astrophysics were Vitaly Ginzburg and Iosif Shklovsky. For instance, Iosif Shklovsky first explained radio emission from sun, from this synchrotron emission, then later he explained emission from Crab Nebula in very wide frequency band with synchrotron emission. So, but also VLBI, the idea of VLBI was introduced by Matvienko, Sholomitsky, and Kardashev, and first experiment was done in 60s with American radio astronomers. And here also I would like to emphasize importance of international, let us say, interaction and conversations in conferences. For instance, almost 60 years ago, it was GEA conference in Jablonne in Poland. And here you see Simch, very famous Irish expert in general relativity. And here you could find picture of Roy Patrick here. And here also you could find Leopold Tinfeld and Vladimir Fock, famous expert in general relativity. But at this conference, Vitaly Ginzburg delivered a plenary talk about astronomical evidences for general relativity. About shadows, one of the first pictures on the subject was published by Jacques-Pierre Luminet. And also there is a critical, let us say, notation was given as critical parameter which separate capture and scattering of photons in this picture. And also that is illustration of this picture. And 20 years ago, Falke, Melia, Arguelles considered formation of shadow in different spectral band. Here you see millimeter frequency, millimeter wavelength, and also centimeter. And so there is a significant scattering in centimeter, and so there is no chance to detect shadow for this frequency band. Around 20 years ago, Russian astronomers was preparing a radio astronomy mission, and PI of this experiment was Nikolai Kardashev. And also that is this mission, it's a space ground interferometer with very high angular resolution. It's not visible, but it's around one at frequency at wavelength around 1.3 centimeter. Angular resolution is around 7-8 microarc second. It's comparable with event horizon of for M87 and Sagittarius A. And our proposal, so that is since angular resolution is around 8-10 centimeters, so we could claim that it's possible to detect this shadow. And what about measuring black hole parameters for the galactic center from this shadow? It's closely connected with theory developed in Chandrasekhar book, because in Chandrasekhar he considered critical parameter which separates scatter and capture of photons. So as you know, photon trajectories, geodesics, are determined only with two parameters. Chandrasekhar called it eta and psi. And so that is critical parameter which separates scatter and capture. And also he reproduced this picture, this parameter. Assume that there is a bright screen behind a black hole, and in this case, so observer could detect this dark region. Now it's called like shadow. And also you see, it's practically also the first time this picture was published in James Bardeen paper in 1973. So, but also it's connected with my old paper. So there is separation of shadow and scattering for, let us say, massless particles here. And if slow-moving particles, also very similar picture. But again, so it's in Chandrasekhar notation. So it's if you write this parameter, so inside gray region you have capture region, and outside is scattering. And there is a critical, let us say, parameter. That is parabolic curve. It's well-known curve for Schwarzschild. But important thing that maximum value for these all parameters is 27. And so also you see if our observer is located in equatorial plane, there is opportunity to detect this shape of shadow. And also it's important thing that its maximum value is 2a. It depends on spin. In this case, there is opportunity to detect this kind of shadow. That is for polar position of observer. It's also for intermediate case of spin parameters 0.5, and also for extremely rotating black hole. In this case, there is opportunity to detect this size of shadows. And so in this paper, we also noted that since there is significant scattering and centimeter band, probably there is opportunity to detect shadow with future missions like millimetron and sub-millimetron missions. So no doubt that shadow will be detected, as we wrote 16 years ago. Again, about simulations, shadow, Miller reproduced this type of shadows in computer simulation in his computer. And here, if observer could detect this size of shadow, then we could conclude that is probably our observer is located in equatorial plane, and also spin is very close to 1. And also about interesting case about Reissner-Nordström metric. Because for Reissner-Nordström metric, we have analytical expression of size of shadow as a function of charge. As you remember, Professor Ruffini considered black holes with significant charge, but this may be important in this case. For instance, for Schwarzschild case, everything is known, is a radius, is square root of 27 in m units. But if we consider extreme charged black holes, in this case, size of shadow started to be much smaller. So it has to be only 4 radius. So, but again, we promote this idea to measure parameters of black holes with this opportunity. But also interesting opportunity was considered by Ben Noon and other co-authors. They said that Randall syndrome suggested their theory with extra dimension. And this theory with extra dimension has so-called Reissner-Nordström solution with tidal charge. In this case, Q squared may be negative. And in this case, we also could consider this case, and also we could say that significant negative tidal charge has to be ruled out. Again, it's but since there are some constraint on size of shadow for Sagittarius A, some models for tidal charge has to be ruled out. And also, I summarize these claims here. But what about observations? Let us see. 13 years ago, Event Horizon Telescope team claimed about Sagittarius A that size of black spot shadow is 37 plus 16 minus 10 microarc second. Is intrinsic diameter of Sagittarius A. It means it cannot be with size around 80 microarc second, as Ben Noon suggested, for significant negative tidal charge. About pictures of black holes also is important because, you know, very often people are using wrong picture for black holes. Why it's wrong? Because you cannot be hidden behind a black hole because strong gravitational lensing. Very often people use this picture, even in Nature magazine. But also here, it's a picture from Interstellar movie, which was done under supervision of Kip Thorne. But here you see shadow. It's visible here. And it's also here you see shadow here. And also that's a picture of, let us say, accretion disk near the black holes. It's always, you cannot be hidden behind a black hole. First people who considered this case were probably Cunningham and Bardeen, it's from their paper. What about Event Horizon Telescope data? Their observations, practically, since they used interferometer, they measured, let us say, Fourier harmonics, and after that, they tried to reconstruct the objects, and the most likely, let us say, conclusion this value. And that is M87, and also their results, size of shadow 42 plus minus 3 microarc second, and mass of black hole 6.5, 10 to the 9 solar masses. But remarkably, we could claim that in spite of angular resolution of Event Horizon Telescope, around 25 microarc second, they reconstruct shadow with this size. That is progress of this project, Event Horizon Telescope, that is a repetition of this project. And but also, I would like to remind you that is dependence of size of shadow is a function of charge. And recently, in this year, Event Horizon Telescope team claimed constraint on black hole parameters, including charge. They considered charge in more general ways, some parameters of spherical symmetrical black holes. And also, that is here, they considered blue line is Reissner-Nordström metric. So, sorry, Reissner-Nordström metric is in consistency with our formulas. But gray region is a variable region for parameters of black holes. So, but in this case, we could say that is parameters of let us say, charges. So maybe only in this region, because there is constraint of size of shadow for these let us say, from these observations. That is the illustration from press release of Event Horizon Telescope team. So that is allowed region, that is size of shadow. So it means that is since shadow is inside, we could exclude this let us say, region for parameters of shadows. Again, from my recent preview, so if we consider also tidal charge, in addition to normal electric charge for Reissner-Nordström, we could also reject some parameters, values of parameters of negative, let us say, Q squared. So it's let us say, charge has to be more than minus 1.22. So, and also there are important observations of polarizations and also magnetic field reconstructions from these observations. And summarizing, we could say that is geo-predicted structures of darkness, while observations we could detect only brightness due to synchrotron emission, and there are a number of models for accretion. And Event Horizon Telescope showed that shapes and sizes of shadow are weakly dependent on assumptions on accretion flow. And many years ago, we said that is in millimeter and sub-millimeter bands, there is opportunity to detect phases around the black holes. VLBI systems in millimeter bands detected shadow around the supermassive black hole at M87, in the center of M87. And shape of images give important information about black hole parameters. Significant tidal charge of black hole galactic center at center of M87 excluded in observations, and also quantum tidal charge could be constrained at M87 and Sagittarius A. So we hope that Event Horizon Telescope will release new image of supermassive black hole, the galactic center, shortly in 1.3 centimeter wavelength. So it seems to me that my time was finished. Thank you very much for your kind attention. Thank you.
Thank you for keeping time. So this is time for questions. There any questions from the audience? There's any questions?
Well, maybe first of all, I enjoy to see the beautiful historical reconstruction with the beautiful pictures of some of the major interpreters of synchrotron radiation, including Shklovsky and
Yes.
All the founding father and certainly this is very important. You also mentioned the work on the charge solution, and I just want to attract your attention to some recent work that we have done, which are published in Astronomy, Astrophysics, and about the possibility not to have a charge, a classical charge, but to have an effective charge, which is due to the magnetic field and the spin of the black hole as a result of our solution, of the gold solution. Therefore, I invite you to look at this possibility, because to us this appears to be very exciting for the structure of M87 as well, and in gamma ray burst.
Thank you. Okay.
Vitaly, thank you for putting our this beautiful picture of Vitaly Ginzburg also. I have a beautiful picture of Vitaly and Zeldovich, atom of Lifshitz. I will send you as an exchange of this beautiful picture that you have shown today. Well, anyway, coming back to physics, well, there is this possibility in the core of a black hole rotating with magnetic field to have not a charge but an effective charge. Therefore, this will be very interesting to keep the mind open, because that could be very important.
Thank you very much. For me, it's a special pleasure and honor that you to mention that the importance of this issue, but because it's because these two persons, I mean Vitaly Ginzburg and Josip Shklovsky, let us say, conducted a lot of studies on the importance of synchrotron emission in astrophysical objects. But also for us, it's let us say, it's not important origin of Reissner-Nordström metric or its generalization. But here I would like to emphasize that important thing that there is simple analytical expression for radius of shadow as a function of charge. It's maybe generalized for tidal charge, but also recently, Hardetsky theory is very, let us say, popular. And that is scalar version of scalar tensor theory. In this theory, there also parameter which looks like, let us say, charge in Reissner-Nordström metric could arise. This is due to interaction, coupling of, let us say, scalar and tensor modes. So it's also, if we believe that Hardetsky theory is correct, it's maybe, let us say, reason why it's rise for this case. But that is very interesting. But also there are, let us say, concerning electric charge for galactic center, there are very contradictory conclusions about this value. That sometimes some people are saying this is almost negligible, but sometimes it's maybe significant. So there is no well-established opinion concerning the issue. But anyway, I would like to thank for your attention and for interest to this issue. But thank you very much again.
Thank you. I would like to make a comment myself about this. Besides the effects of the black hole properties itself on the shadow, probably most of the most important points or critical points on the calculation of this is the environment around the black hole. There are a lot of uncertainties both on the density and the enormous radiation that can be around the black hole, and these are critical points in the determination of the shadow.
Yes, everything is very important, but also it's in this case, these conclusions look like model dependent, because our knowledge about accretion, in spite of great efforts, our knowledge about accretion character just near compact object is not perfect, let us say. But it's but remarkably, that is Event Horizon Telescope observations confirmed very simple conclusions about character of gravitational field at M87. So that is nice.
Thank you. So we end our session, I guess. We don't have more speakers, and we are perfectly on time. So I would like to thank all of you, to thank the audience for your patience, and the speakers. To all of you have been very strict on time, and so that is very good. So I don't know if Surush is going to make an announcement on anything, or
just a very short comment about the starting time of the next session. Will be started at 3 p.m. Iranian time and 12:30 Central European time, or let's say Italian time.
Thank you again.
Thank you.
Thank you so much.
Thank you. See you later. Bye bye.
See you. Bye.
Bye bye, guys. Take care.